Okay, we're going to be talking about a couple of different things. The first thing we're going to review are some basic trig integrals. And we're looking at the indefinite. We're going to fast forward to definite integrals, but this is just a little review in case you don't know the rules for trig functions and integration. So first thing we'll start off by saying is that if we have the integral, suppose of cosine, well, when you integrate cosine, you get sine. All right, when you integrate sine, you get negative the cosine. When you integrate secant squared, you get tangent. When you integrate secant tangent, you get secant. When you integrate cosecant cotangent, you get the negative cosecant. And it should make some sense because right off to the side here, if you notice, oh, and I forgot the last one, cosecant squared is negative the cotangent. So it should make sense because look at the derivative rules. Remember that an integral is exactly that, an antiderivative. So we're working backwards. All right, so that's what's going on here. Well, now we're going to take this and we are going to apply it to a really important theorem, and that is the fundamental theorem of calculus. And let me pull that back up. Give me 1 second. I don't know why it disappears sometimes, but we're going to apply it to something called the fundamental theorem of calculus. And so what happens here, it says if f is continuous at every point in a closed interval from a to b, and then most importantly, that capital F here, all right, is any antiderivative of little f, lowercase f, which is the function, on that same interval. Then what happens is you would take the antiderivative to get f, you would evaluate it at a and b respectively, and then you would find their difference. Okay? So this right here is the evaluation portion of the fundamental theorem of calculus. All right, another name here, some books will call it the integral evaluation theorem. So it's real simple. You take the antiderivative, you plug in the limits of integration, and you find the difference. Okay, let me repeat that one more time. You take the antiderivative, all right? You evaluate or plug in the limits of integration, and you find the difference. Okay, so that's in a nutshell what the fundamental theorem of calculus evaluation part means. All right, so let's go ahead and take a look at a few examples where we're going to apply what we just learned, all right, in finding an antiderivative. All right, these are really nice and they should be really quick. All right, on these trig, you do need to know the unit circle. So I'm going to assume, of course, you know what happens when you assume, but I'm going to assume that you know what's going on when I'm referring to these radian values. So first thing I'm going to do is I'm going to take a look and see that I have 9, a constant multiple or a scalar multiple, and I'm multiplying it by sine. And the integral of sine from my chart over here to the left, or to the right I should say, is negative cosine. So I'm going to write out negative cosine, all right, of x. But now I need to also remember that I have a 9 being multiplied. So I'm going to write negative 9 the cosine. Now I do not need to write the constant of integration because this is a definite integral. So what I will write is my evaluation bar here, and I will evaluate it from 0 to pi. All right, so what this means is that I'm going to find, if this is my capital F of x, I'm going to find f of b and subtract f of a. This is the fundamental theorem being applied. Okay, so let's go ahead and do that. So I'm going to say, well, I have negative 9 times the cosine of pi minus negative 9 times the cosine of 0. And so the minus minus makes for plus. And now what I'm going to do is I'm going to substitute what I know to be cosine of pi from the unit circle, negative 1, and cosine of 0, positive 1. And so when I do that, I get a negative 9 times a negative 1, which is positive 9, plus 9, all right, which is my final answer, 18. 18. There it is. Okay? So now we look at the next one, number 5. We're going from negative 7 to 5. Those are my limits of integration, and I have e to the x that I'm integrating. Well, think about this. If you remember the derivative of the exponential function e to the x, it was its own derivative. So it makes sense that its integral is exactly itself. So when you integrate e to the x, you get itself e to the x. And so we write our little bar here, our evaluation bar, such that x will take on the values negative 7 to 5. And now we are ready to plug in through the fundamental theorem of calculus. And that is to say, e to the 5th minus e to the negative 7th. And I mean, this answer is good enough, but you can go one step further, clear up those negative exponents, and you can write it as e to the 5th minus 1 over e to the 7th power. And you get something that looks like that. Okay? You get something that looks like that. All right? So, all right, here's the point where I'd probably ask, are there any questions? But what I would do if you're a little bit lost, a little bit confused, pause, rewind. If it's going good, fast forward. But let's go ahead and take a look at a couple more examples here. All right, so we've got this next one, and this one is nice. It's kind of just a regular algebraic function. We take the antiderivative with the power rule. So in this case, I'm going to have 3x negative 4, and I'm going to say plus 1, because remember, you always add 1 when you take the antiderivative. That gives me a negative 3, and then I'm going to divide this by negative 3. And so I end up with something that looks like, well, I can't forget my bar here, negative 2 to negative 1, but I'm going to clean it up just a little bit, okay? And that is to say that it's negative 1x to the minus 3, evaluated from negative 2 to negative 1. And so what I'm going to do is I'm going to write it using positive exponents, negative 1 over x to the 3rd power, evaluated from negative 2 to negative 1. And now I'm ready to evaluate or plug in. All right, so this one's not that bad. What does it look like? Negative 1 over negative 1 to the 3rd power minus another negative 1 on the top, and then a negative 2 to the 3rd power. So when I evaluate this, I end up with a negative 1 over negative 1, which is a positive 1. All right, plus, because minus minus makes for plus, but it ends up being negative because I have a negative 2 in the denominator to the 3rd power, and that becomes an 8. Negative 1 over 8. So 1 minus 1/8, in other words, is 7/8. All right, 7/8. All right, any questions? Nah, I don't think so, because you're on YouTube here. All right, so let's go ahead and take a look at another one here, another nice example. This one combines a number with trig. It's really nice, okay? When we integrate a constant, like 10, we end up with 10x, okay? 10x. Plus, all right, the integral of cosine, well, from our chart, that's really easy to figure out. It's just sine of x. And so now I've got this, and I evaluate it all from negative pi over 2 to pi over 2. And this is why having that unit circle memorized is so important. So let's go ahead and see what that looks like. So this is going to be 10 times pi over 2 plus sine of pi over 2. All right, all of that minus, then it's 10 to the times negative pi over 2 plus sine of negative pi over 2. And now I'm ready to substitute in the values that I know from the unit circle. So 10 times pi over 2, that's not a unit circle thing. That's just straight up multiplication, 5 pi. Sine of pi over 2 is a positive 1. This one right here gives me a negative 5 pi. And sine of negative pi over 2 is a negative 1. Okay? So I end up with something that looks like this. 5 pi plus 1 minus negative 5 pi minus 1, and I can distribute that negative sign. I end up getting 5 pi plus 1 plus 5 pi plus 1, which ends up giving me a 10 pi plus 2. All right, nothing to it. Some simple unit circle stuff, some simple addition and subtraction. All right, and integer operations. All right, last example then of this variety here, number 8. And I think it's a really nice problem, okay, because this one is a power rule, and those are so easy to use and apply. The problem's going to come in the actual evaluation, but I'll tell you what, right, when you get this one, don't fear, don't fret, just figure this one out at the very end with your calculator. Give me 2 decimal places, and that's what I'm going to do here. All right, so we are going to apply the antiderivative power rule here. We have 2x to the 4th power divided by 4, because you add 1, remember, minus 8x to the, in this case, negative 1, and then divided by the new power, negative 1. So then we evaluate that from 1 to 3. Well, we can clean this up just a little bit. 2/4 becomes 1/2. 1/2 x to the 4th power. Minus minus makes for plus. All right. And then we have 8x to the negative 1. And actually, I'm just going to write this as 8 over x, because that negative 1 means it goes in the denominator. And now I'm ready to evaluate it from 1 to 3. So let's see what that looks like here. We have 1/2 of, I like to use square brackets here. 1/2 of 3 to the 4th power plus 8 over 3. All right. Minus, and I have 1/2 of 1 to the 4th power plus, in this case, 8 over 1, which is just 8. All right, nothing to it there. All right, so 3 to the 4th power is 81 over 2 plus 8 over 3 minus a 1/2 minus 8. Okay, and you can do all of this fancy stuff on the calculator. Nothing to it really. So I'm just going to tell you what the final answer here is. When you do these operations here, it's about 34.67. So that is the answer. Okay, and we did this all by hand. We didn't need to use a calculator or anything. I mean, you could use a calculator for this, but why? You need the practice. Okay, you really do need the practice. All right, so some really nice solid examples on applying the fundamental theorem of calculus. Remember, when you're working with the fundamental theorem of calculus, the idea is you take the antiderivative, you evaluate it at the limits of integration, and then you find the difference. Okay, so that is the fundamental theorem of calculus, integral evaluation theorem. I hope this video was helpful, and as always, like and subscribe.